Hello everyone. Our project is drought risk prediction using remote sensing datasets in Texas, presented by Gunush, Rina, Mongjie, and Arif. Drought can lead to widespread and far-reaching environmental, social, and economic impacts. In agriculture, droughts can reduce the water availability and quality necessary for productive farms, ranches, and grazing lands. Cotton is a top field crop in Texas. With adequate irrigation, cotton can be grown in dry areas. Therefore, the goal of our project is to predict the degree of drought by using multiple linear regression models in order to irrigate cotton farms in a timely and correct manner. We selected two research areas according to cotton production. The first area includes 9 counties, which are in the top 10 cotton yields. Nueces is also in the top 10, so we designate it as Area 2, along with the other 3 surrounding counties. There are some literatures that use multiple linear regression to predict drought in other areas. Kim developed a multiple linear regression model for 4 kinds of drought index estimation by using remote sensing and climate data in South Korea. The performance of the 3 indices models were significantly higher than the other model. Seibert used ANN for seasonal forecasting of drought in Africa and compared the model with multiple linear regression and random forest regression tree models. The results show that multiple linear regression is the best, while the others were likely to suffer from overfitting. This study explored the ability of several models based on penalized linear regression and decision tree-based ensemble methods to predict drought conditions in northeast China. The prediction results indicate that the penalized linear regression models provide better prediction results. There is a paper about the drought category prediction using logistic regression in Texas. It integrated the USDM drought category with drought information from other sources. The proposed model performed well in predicting drought categories and can add early warning for drought preparedness plan. Multiple linear regression was also used to find out the relationship between drought and yields. This research investigated the effect of different drought conditions on barley yield in USA by using multiple linear regression and ANN. In this paper, ANN is proposed as a viable alternative method or in combination with multiple linear regression to investigate the impact of droughts on crop yields.
Hello everyone, this is Arif speaking. So I would like to talk about the data we gathered for drought index modeling. Based on the literature review, we consider 4 variables such as precipitation, temperature, vegetation index, and evapotranspiration. So as you can see from the metadata, that drought index and precipitation were collected from land-based station. We can see the figure. The station spread it all over United States, especially Texas state. Also, we provided the source to download the data. And for the temperature, vegetation index, and evapotranspiration, we were collected from remote sensing based satellite, particularly from MODIS satellite. It has a different resolution, 250 meters and 500 meters, but we consider it's okay, suitable for monitoring county areas. Here we collected the drought index from the United States Drought Monitoring website. This is an effort from the NOAA and USDA. The website provide the time series drought. Also, the website provide the visual drought over the study area. For precipitation data, we collected from National Center for Environmental Information from National Oceanic and Atmospheric Administration, or NOAA. Here's the example for the Lubbock County from January 2000 until January 2023. This precipitation data was based on the PRISM algorithm. And for the another variable, we consider remote sensing data because the advantage of the remote sensing, such as the ability to collect information over large spatial areas with, with their changes over time. This is the website where we collected the MODI satellite. And then this is the example of the result over the Lubbock County. This is NDVI, Normalized Difference Vegetation Index from 2000 until 2023, matching the time frame. So because our data have different frequency, monthly, biweekly, and weekly, we should match our data, and we consider monthly data as for the drought modeling. We use resampling method using the Python algorithm using pandas, numpy, and the time. So we only extract the date and the mean value from each date, and then we resample to monthly data using resample code.
Hello everyone, I'm Ganesh Tusi. We are talking about our project number 5. As my friend discussed, we have 2 areas to check them, and also we run 3 models. Now I'm talking about 2 models for 2 areas. I start with model 1 for area number 1. Yes. First, we import our libraries and read our Excel files to have our data. And as I start, we check the correlation matrix for all our variables, independent variables and dependent variables. As a quick check, we see that the impact of precipitation on the drought is negative. It shows that as the precipitation increases, the drought will decrease. Temperature has a positive correlation, vegetation has negative, and evapotranspiration has a negative impact. Also, we can see the plot for the correlation. The red points shows that it has a high correlation, and as it goes to neutral colors, it decreases the correlation. To model our data, first we define our independent variables, which are X, and also our dependent variable, which is Y, it's drought level index. And we try to scale them and transform them into normal numbers, so they be same as each other somehow. So we start with test and training. As we know, we first choose a part of dataset to train them, and after that we test them. Here, normally the test size is between 20% up to 30%, and we choose 20%. And then we run some stat model to have a model for our training dataset, and we run the summary of model as below. What is important in our model is R-square, which we can see that it's 0.2. It is somehow good because if R-square is normally between 0 and 1, and 1 is the perfect model, but R-square is good. And also we can see the coefficients, which is the constant, and coefficient for each independent variables. And the standard error shows how precisely we have estimated them. We also can see the Durbin-Watson, which is below 2. And below 2 means that the residuals have a positive relationship. And also after that, we calculate our errors, MAE, MSE, and RMSE. All of them are equally like between 1 and 2. And it's based on our every model, it shows a good number. After that, we plot our data and our predicted data, which we predicted, and it shows a straight line that goes through the observations. We did the same for the second area, and in the second area we did all the similar to the previous one, and we checked the correlation matrix, correlation heat map. And after that, our data, the R square is 0.183. And here our Dewey Watson is 2.0, which is more than 2. So it has a negative autocorrelation between residuals. And then we train and model that and plot the predicted line. Our second model is like the previous one, we just read the CSV and we plot the correlation matrix and the heat map. And after that, we test and train. But here we used scalar predict models, and we plot the line through the observations. And also we did the same for our second area, and we see the results are okay, and the plots.
Hello everyone, I'm Reena and I'm going to talk about the logistic regression model we created for the drought prediction in two of the areas within Texas. For the logistic regression, first we imported all the libraries we need to perform our logistic regression, and then we set our working directory for the area 1. For the x variables and y variables, we selected precipitation, temperature, vegetation, and evapotranspiration as our x variable, and drought level index as a y variable. We then normalize our x variable and we change our y variable to binary variable with a threshold of 0.84. We then split our variables into train data and test data. We then for the logistic regression, we then set a large C to ensure no regulation, and then we fitted the model to training data, and then we predicted our training data and testing data using the logreg predict function from the scalon model. And then to evaluate the performance of the model, we get the parameters using the logreg functions. Then we extracted our coefficients and intercepts and saved it in a separate variable called vals. And then to evaluate our the performance of our model further, we created confusion matrix for train data and the test data. For the confusion matrix, since our true positive and true negative are higher than the false positive and false negative, we can say that our model is moderately good. And then to further evaluate our model, we check the accuracy of our model, accuracy, precision, and recall of our model. The accuracy helps us to tell how often our model is predicting the values correctly. Then we plotted the ROC curve of our model. The ROC curve gives us the area under the curve. The area under the curve is 0.7. So in the range, it's above 0.7 for both the models. For both the areas, the ROC curve is the area under the curve is 0.7, above 0.7. So we can say that our model is performing moderately good. Although it is moderately good, we cannot say that our model is perfect, but still we can use this to predict our drought, predict the drought for these areas. By doing some optimization, we can use this model and improve its performance.